before we get started this morning, let me just go over a few things. Now, number one, see, what is it? One or two people have turned in papers so far. Last day to not lose points is Monday, okay? I will accept them after Monday, but you'll be losing points after Monday. You can still get one bonus point turning in today or tomorrow, but then starting Monday, you get no bonus points, you just get your score, and then after Monday, you are losing points. So, and this class, I think, okay, one guy I think is not coming back. Another one did turn in something last time, so I can turn back to you your first test. I'm sorry it's so late in the term to do that, but here is your first test. Chris is not here, Khalil is not here, Kayla's not here, Colton is here, and I think I already returned Peyton yours to you, didn't I? Yeah. All right. So I did that when the other guy returned his in finally. I got those back to you. So that was also a marking of the roll. Peyton's here and Colton's here. Okay. That's all she wrote. Okay, your second test, I think maybe one or two people have turned it in and that's all. So I do need those in by Monday as well. So if you haven't done the paper yet, the paper and your second test, I think I recall saying early in the term, don't put things off till the end, but that usually falls on deaf ears early in the term. Okay. And we will have class. We have class today and class on Monday. And then at the end of the class on Monday, I'll give you your final. It'll be a take-home. Oh, and by the way, I should have said this in my last class. I forgot to. From what I understood from some other students, they have open student course evaluations for summer. Have y'all seen that? It's an online thing. You will. Do you check your Lawson email at all? No. Okay. Please go out and check your Lawson email. And even if you can't get to Lawson email, what you do is go to the Lawson State web page, and unless they changed it, when you get to the Lawson State web page, on the home page of the web page, there are a series of tabs, blue tabs at the top of the page. And near the end of the page is one big bright yellow tab, okay? And it says, quickly, I think it is. I think it says quickly, something like that. If you click on that one, then you get a whole menu here. Scroll down through the menu until you see something that relates to student course evaluations or student evaluations or something like that. The name of the package is called Smart Eval. So you may actually see that. SMARTEVAL, written as one word, Smart Eval. But look for anything that relates to that, and when you see that, click on it, and then it'll tell you how to proceed. Pretty sure you'll need your student ID number. That's a 7-digit number, probably starting in the 120s or something like that, and then 4 more digits at the end of that, 120 or 12 something, and then 4 digits after that. And I think your login, your password is in, I think, your birth date. And I believe it's 2-digit month, 2-digit day, 2-digit year. But I think they have a little prompt there that tell you what order to do it. I don't think it's a 4-digit year. I think it's just a 3-digit year. But look at the prompt. You're used to doing these kinds of things, and you do the student course evaluation online. So please get those done. preferably by Monday, so when I ask on Monday, they will be done also. All right. Can't think of anything else. Do you have any questions before we proceed with this?
Do you know anything about how we go about getting our transcripts sent back to our schools?
Okay. I can tell you where to go to do it. Now, I know there's a transcript request online, and that may be exactly what they tell you when you go down there. But go down to the registrar's office. You know where that is? Okay. And go in and ask one of them, and I bet you they'll say, you can do it online. But they have a computer set up right there on the counter. You can do it online then. So if you have any questions, you can ask them, and they can help step you through the process.
Go ahead and request now before final grades and all are put in?
Again, that's a good question to ask them. I don't think it really matters when you put it in, because I believe you can put it in now, and then as soon as all the grades get in, it will be done. But ask them that, and if they want it, request after the grades are in, then again, get them to help you step through, make sure you got everything, and get that done. But I believe they'll take those requests early. They just can't send them until they get all the grades. Are you taking 1 or 2 classes here or more? Just 2. Okay. So yeah, check with that. Good question, by the way. Should have, well, I'll hit the other class on Monday when we meet. But those are, it was like this class, so few students to begin with, I didn't do all those at the beginning, and then I forgot to later when people came in. Okay, any other questions? Good question, by the way. All right, where we left off last time was figure 3 at the top of page 515. This is chapter 10, infinite series. 10.1 is sequences. And we were talking about the convergence of a sequence. And if you were to plot the various terms of the sequence, and even though there may be wild swings to begin with, but after a while they start narrowing in on something, and it looks like that's something the values are getting closer and closer to. If there is some, whatever that something appears to be, we'll call it L, the limit now, if after a certain term in that sequence, all the others stay within any arbitrarily small value epsilon, then we say that that sequence converges. And if you want to make sure of that, just pick a smaller epsilon, and then you might have to go to a larger value here, further along down the terms until you get to one, and then it all stay within that one. It converges. So for an arbitrarily small L. So this is the plot of the sequence of a limit L. For any epsilon greater than 0, you choose, okay? If you can get the dots eventually to remain within the epsilon band around L, then that sequence converges. Okay? This is a graphic of example 3, so let's do example 3. I don't think I'll even blow up the graphic. It says, let A sub n, let me get my pen activated again. Let A sub n equal n plus 4 over n plus 1. Okay? It says prove formally that the limit of A sub n as n approaches infinity is equal to 1. It says prove it formally. Well, you can go back to the definition of a limit, and you can do it that way, and that's how they want you to do it. Okay? But here's actually the better way, I think. Okay? Is, let's write that limit down. That'd be, oh, this is A sub n. All right. The limit of n plus 4 over n plus 1 as n approaches infinity. Okay? That's what it's asking for. Well, let's see what that is. Here is the trick. Multiply and divide the numerator, divide the numerator and the denominator by the same number, which is 1 over n. Now, 1 over n, it cannot be 0 in, okay. First, n's not 0 because n's going to infinity. So, nowhere close to 0 there. But because there is no infinity, even though n going to infinity, 1 over n is approaching 0, it's never 0. Okay? So this is a legal move. You can't divide by that number because it's never 0, even though it's getting closer and closer to it. And if you do that, look at what happens. This becomes, I'll write the limit again. Limit as n approaches infinity. And this becomes 1 over n times n would be 1, right? Plus 4 over n over 1 over n times n is 1, plus 1 over n. Same n, okay, right? Now, what's the limit of that as it's approaching 0? And it's approaching 0. What's 4 over 3 million? Pretty small number. Is approaching 0. 1 over 3 million, approaching 0. Okay? So, the second term on both of those are 0, so that's approaching 1. Now, that's not really how they wanted you to do it. They wanted you to use the epsilons and that kind of stuff, but my word, this does it much neater, better, and to me is just as formal. I don't know if they consider it as formal. But if you look at how they proceed, well, they don't proceed, do they? Oh, here they do. Okay. They start with this. Remember the limit. All right. Remember what it says. The limit as a sub n, as n approaches 0, of a sub n is that limit L, which we think is 1. That's what they say to do. Then a sub n minus 1 should be less than infinity. We got Chris here. All right. Now I did return last time test 1 because I finally got the last test 1 in. So there's your test 1. And test 2 I will take any time. A few people have turned it in so far, but not that many. Here's the other thing. I knew there was one other thing I meant to say. So time out from this. We'll get back to this in a second. I apologize for not, well, phrase it this way. I apologize for having that much grading to do, okay? If you haven't seen any grades go in Blackboard lately, it's not because I haven't graded stuff, it's I haven't had a chance to do so. We had what was called our planning hearings yesterday morning. Technically supposed to start at 10. And I had been working on those for, not very rigorously, but working on them for well over a month, but trying to get data from the other instructors and stuff. That was the hard part. And last week, I stopped everything else, including grading, and worked totally on that. And, well, I had students come by for registration and advising and that. Couldn't help those. But all my spare time except for that, which I don't have much this summer, all my office hours were eaten up doing that, especially last Thursday. So I got 0, well, Mondays and Wednesdays I have no time to grade at all because I'm in class from 8 in the morning till 9 in the evening with 2 20-minute breaks and 2 10-minute breaks. So don't have any time for grading then. So Mondays and Tuesdays and Thursdays from 10 to 12 and 3:30 to 5:15, those are my only office hours. So I usually take stuff home. But Thursday, that's all I worked on was the planning hearing, trying to get it in final form. And I didn't get it finished because one of the instructors didn't get me his data in time. He got me his raw data, but no documentation. So I was able to work then on the, what should we call it? Well, he actually got it to me on Friday, the raw data. So I had to spend the weekend incorporating his stuff in with the others that I'd already been putting together. And finally got everything completed late Sunday and got it sent to the people it needed to be sent to, but he still hadn't gotten me the documentation. So yesterday, rather than having any time to do anything else, I actually had to cancel my, postpone my differential equation class because I had to go to Birmingham campus, get his documentation, put it in a notebook, and be ready for the meeting at 10. It all went well, but basically that ate all my office hours yesterday as well. So finally yesterday afternoon, I had a small amount of time to work on grading. I got a little bit graded, but most of it was spent getting ready for final exams. So it's all come at the end of the term, and it's kind of nuts. So if you haven't seen anything get out there lately, it doesn't mean I haven't gotten it graded or that I'm not going to get it graded really soon, but tomorrow is the earliest I can. So tomorrow morning, 10 to 12, if I don't have many students come by, hopefully I can get some done then, and then tomorrow afternoon, especially from 3:30 to 5:15. Other than that, it's going to be the weekend. So I'll be all weekend probably getting all those papers graded for that. So anyway, you should see the grades show up sometime into the weekend. The grading comes first, then the entry on Blackboard comes next, and then the attendance goes next, and I hope I'll be ready for the final exam on Monday. Okay, and I will be, okay, Khalil's here. Okay, and I did return to everybody who was here Monday. Good deal, thank you. Here, if you'll wait just a second, your right class. First test. And I've only received a few of the second test, and I was just telling the others, because we had a big deal planning hearing yesterday, I got no grading done from basically from Tuesday afternoon of last week until now, okay? And won't have any done today, but, well, I got some done yesterday afternoon, but not too much. Nothing will be graded pretty much until tomorrow morning, okay? So at 10 o'clock. So hopefully, well, no, actually, I'm going to have to take up part of my grading time tomorrow because making up for the class I missed in differential equations. So it won't be until tomorrow afternoon that I get anything graded. And I'll get started then and take it home over the weekend and wrap it up over the weekend. I should be able to return everything to you on Monday, which means your second test, which means I don't have many of them yet, so get them in. If you turn them in Monday, that'll be fine. I just won't be able to return them to you. And then at the end of class, we're going to continue wherever we leave off today. We'll continue class on Monday, and at the end of class, I'll give you your take-home final, which basically is going to be Chapter 8, the 3 sections we did there, Chapter 10, the 2 sections we're going to do here, and whatever we get covered in 11. Okay. Now, technically, we should have gotten into 12. I don't think we're going to make it, and hopefully when you get back to your home institutions, that won't sting you too bad, okay? But I think you've got all the foundation that you need. You just have to get caught up in anything that we didn't get to cover in class. Losing, I think it was 3 Tuesdays, did not help us at all, okay? I mean, 3 Mondays didn't help us at all. I was saying 4, but they are giving us this coming Monday as a makeup for one of those. But I had the vice president scheduled us for a trip on Monday, Tuesday rather than Friday, Saturday. That cost me a Monday. Then 4th of July, they did a Monday. So Seems like there was one more, and I don't remember what that was. But anyway, sorry about that. It was not a 10-week term like it should have been, more like an 8.5-week term. Okay, so let's move from there. Okay, so that's how they wanted you to approach that, the limit I just did. I found it far easier to see and just as thorough and, what do they call it, formal as what they are doing. Okay, so let's move on to this. Now there's one figure that's in your book that's not in this one, and this is figure 5. And I'm trying to see where they refer to it. There it is. There are some functions that do not go to infinity. They don't blow up and take off and go either to positive or negative infinity, that still have no limit. And one of the examples of that is this one. Okay. A sub n is equal to cosine of n. Okay. And n can go wherever you want to. I mean, pick an n. I would say keep it either 0 or positive. But if you're starting with n equals 0, cosine of 0 is 1. Cosine of 1 is cosine of 1. Remember, you're in radians, and that would be 1 radian. That's close to 60 degrees. It's not exactly 57.8 or something like that degrees 1 radian is. So you're starting at 1. You go somewhere down here, then you go somewhere down here, and then somewhere up here. And you do this. You're just picking various n's on the cosine curve, and it's always between -1 and 1. And it stays between -1 and 1 as far as you go. So even though that doesn't blow up and go to infinity or minus infinity, it always stays between -1 and 1. There is no epsilon that you can choose that you guarantee you're going to be between it for any epsilon greater than it. You can't do it. So cosine if you thought there was a limit there, 1 or 0 or anything else, you cannot, for any arbitrarily small epsilon, always guarantee it's in between there. Best you could do if that epsilon was 1, and that's not arbitrarily small. That's the only way you can do it. In fact, 1 wouldn't even work because occasionally it does come out being 1. So, no way. Even though it doesn't blow up, those values never converge to any single number. They stay between -1 and 1 with no preference. So that's the figure 5 at the top of your page, 515 on the right-hand side. So now we move to this description. It says we'll often use says about the middle of the page, note the following 2 facts about sequences. The limit does not change if we change or drop finitely many terms from the sequence. If C is a constant and A sub n is equal to C for all n greater than some fixed value capital N, then the limit as n approaches infinity of A sub n is that constant C. Thought they were going to be leading into the next sentence. They really don't. Many of the sequences we consider are defined by functions. Just like that cosine was, that just didn't converge, but it was defined by that. So if A sub n can be written as some function, f as a function of n, something like this. A sub n is equal to n minus 1 over n. Now, what can you tell me about that? Does it have a limit? Almost do the same trick we did before, only this one's easier. You got a monomial in the denominator, right? You can write that as n over n minus 1 over n, right? That's just subtracting, fractional forms. Well, what's n over n? 1. Yeah, anything over itself is 1. And what's 1 over n as n goes to infinity? 0. So the limit of this would be 1. Okay? But you could have referred to that as f of x is equal to x minus 1 over x. Okay? And we'll often use the fact that f of x approaches the limit L as x approaches infinity. Then the sequence a sub n, which is f of n, will approach that same limit L. And if you look up, no, I'm sorry, it's not quite the same. But here's a function. They don't even tell you what it is. Let me blow it up for you. If this was your function, maybe a damped, translated cosine function or something like that, but you have a dampening factor there, and it starts well off of here, but after a while it gets closer and closer and closer and closer. If that is approaching some value L, meaning that there is an epsilon somewhere out here, no matter how small you get the epsilon, if you keep the function, the sequence or the function within the limit of epsilon, then it does converge to L. The dots represent the sequence, the line represents the function. So you can write it as sequence f of n or the function f of x. If one converges, the other converges. That's basically what this theorem says. Okay? If there, the limit of some, the limit of some function as x approaches infinity of some function f of x exists, then the sequence a sub n is equal to f of n converges to that same limit. If it exists, it converges to it. So the limit is n approaches infinity of a sub n be exactly the same as the limit as x approaches infinity of f of x. Okay. So that'll be quite useful sometimes. Okay. So I don't think we have a slide for the next one. No, we don't. So let's use this space here. Find the limit of these sequences. 2 squared minus 2 over 2 squared. Anyone hazard a guess? Very similar to one I just did. You have a monomial denominator, so write that as 2 squared over 2 squared minus 2 over 2 squared. What would this be? 2 squared over 2 squared is 1, and this will be 2 over 4, which is 1/2, so 1 minus 1/2 is 1/2. How about this one? 3 squared minus 2 over 3 squared. What would that be? Now these are not sequences, these are just numbers, okay? So what would this be? Very similar to the other one. 2/3. Okay, is it? Or 2/9? Oh, wait, I'm sorry. Let's just do it. That would be 3 squared over 3 squared minus 2 over 9.
That's the two.
Huh?
That's the two.
Where?
The second.
Yeah, this is yeah, that's a 2. Sorry about that. Is that the one you meant? Sorry about that. Okay. That would be 1 minus 2 ninths would be 7 ninths. So the sequence so far is 1/2, 7 ninths. The next one would be 4 squared minus 2 over 4 squared. And that would be 1 minus 2 over 16, which would be 1 minus 1/8 would be 7/8. Okay? Okay. Next one would be 5 squared over minus 2 over 5 squared. That would be 1 minus 2 25ths, which would be 23 25ths. Okay? So in other words, the sequence here is a sub n would be n squared minus 2 over n squared, right? Every term is, the counter is being squared. Okay, well, what does this turn out being? N squared over n squared minus 2 over n squared, and this would come up to be what? 1 minus 2 over n squared, and as n goes to infinity, what does this go to? 0, big time. So that's equal to 1. So that sequence starts at 1/2, 7 ninths, 7/8, 23 25ths, you know, it keeps on getting closer and closer to 1, but never gets there. So sure enough, that is 1. Okay? Now, looks like to me that was pretty easy to do just with the n's in there. They did it with the x's, which works just the same. And you get the same answer. So I don't see a big advantage in that case of going to a functional form. But they did, and it works. You get the same answer. Okay? Now this next one is example 5. Calculate the limit as n approaches infinity of n plus, no, it's not that one. Yeah, no, it's not. Sorry. Let's go back to this one and clear the screen. I thought it was, but then when I saw it, I said, nope, wrong one. This is the limit as n approaches infinity of n plus log n, that's strange, that log n, over n squared. Okay? Now, that one may be a little tougher to do with just the n's. But in some sense, it's not really too much worse. At least the first part, I think we can. So that would be the limit as n approaches infinity of n over n squared minus log n over n squared. Okay? Well, I think you see what this one goes to. N over n squared goes to Jasmine, right? Okay. And I returned your first test to you last time, but some people weren't here last time, so. What does n over n squared? Limit of that is n goes to infinity. 0, because that's 1 over n, that goes to 0. Now, the question is, how about a minus log n over n squared? that's not quite as easy to mess with, is it? So, I'm wondering if I should have done the first part by itself. But, it seems like to me that you can almost visualize this one. That would be the best way to do it. Log n, if you think about it, basically goes like that. It goes up really slowly, but it's always increasing. N squared goes up really fast. You increase it. So n squared is going to way overpower log n. And that's obviously going to 0 to. I would say faster than this one. Okay? So therefore, I wouldn't worry too much about it. I don't know if they wanted you to do that formally, but just looking at it, that's got to go to 0 as well. Now, yes, okay. But, on the other hand, here's a way to do it more formally than that. And I wish I'd have thought of it. I should have thought of it right off the top, because we just did it in Algebra 1 today. That's a form of infinity over infinity, right? What can we do with a limit that's like that? L'Hopital's rule, exactly. So this will be the same as the limit as n approaches infinity of what? 1 plus 1 over n over 2n. Okay? All right. And this one, the numerator as n goes to infinity is 1, and the denominator is infinity, and 1 over infinity is 0. So that's even easier than, well, I'm not saying it's easier than thinking through it, but it's certainly easy to do fairly formally. Okay? Okay. The next one now is the Balmer series. Okay. Balmer wavelengths. Sequence, you could say. Calculate the limit of the Balmer wavelengths, and the Balmer wavelength is b to n is equal to 364.5, nice round number, n squared over n squared minus 4. So the limit of that, and when you plug in the n's, and by the way, n for the Balmer series, n must be greater than or equal to 3. Okay? Remember, sorry. You can start your sequence anywhere you want to that makes sense. And this makes no sense to start at n equal 2, right? Not defined there. And anything before that would not be very well defined because you have wavelengths with negative numbers. So that's not going to make any sense either. So you've got to start 3 or greater. Okay? And it does work. It does work quite nicely. So at n equal 3, you have 656.1. Because this would be 9 minus 4 is 5 in your denominator, 9 in the numerator. So that just draws this down a little bit. Yeah. No? I do believe, okay, I'll put it on your desk. We did get the first test, the last student to turn in test 1 did so last class, and now I can't find it. Here we go. Somewhere here. There it is. Here we go. There was your first test. And for those who have come in since I said this before, your paper has to be turned in by Monday to avoid losing points, okay? If you turn it in today or tomorrow, you still get 1 bonus point. If you turn it in Monday, you get 0 bonus points, just your score. If you turn it in after Monday, you start losing points. So please get that in sooner rather than later. I've been saying that all term, but it's really come down to the wire now. Please get it in sooner rather than later. I've returned the first test to everybody who's been here to get it, but we're still missing quite a few second tests. Now, I don't have any grades in the grade book yet, but I have started grading some of them. Just I'm behind in that, which leads me to the next point, and y'all have heard it because you were here before. Starting with last Tuesday afternoon, last week, not this week, last week, not yesterday, but last Tuesday, we had a big hearing going on yesterday, and from Tuesday afternoon until tomorrow afternoon, I basically had time to do 0 grading, okay, because we had to get the data for the hearing done. So I'm this far behind in grading right now. I'm hoping to catch up starting tomorrow afternoon. I can't do much tomorrow morning. I can't do anything today because I've got classes all day long. But tomorrow I have to make up the class that I missed yesterday because we had the hearing, okay, and I had to be on the Birmingham campus to get the last of the documentation from the instructor who hadn't gotten it prepared in time. So I'll miss my 10 to 12 office hours tomorrow, and so sometime in the afternoon, starting about 3:30, I will be able to start grading, and I'm going to start grading and grade as much and as hard as I can. It'll continue through the weekend, so by next Monday, I hope to have all this graded. It's going to be a busy weekend, okay? But that's the end of the term. Then on so I want to return everything to you. I can't. I cannot return your research paper because periodically they do ask for samples of student writing, so I have to hang on to that one. But your first test, I've given all you that back. One person hasn't been here to, well, a couple people haven't been here to get theirs. And then the second test, only a couple people have turned that in, and I don't have those graded yet, but I will have them graded by Monday, and I'll turn them back to you then. But that means all the rest of you have to turn in your second test before I can give back that one to the others, or else it goes down as a 0. Because once I return the papers, I can't receive any more in. So please get them in on Monday. Okay, test 2. I'll be giving you test 3, which will be your final exam. It will cover what we've covered in chapter 8, 1, 2, 3, 10, 1, and 2, and whatever we get covered in 11. Okay. That's today and Monday. We'll continue with this then. So here's your Bomber series, and there's something that's I'm having trouble when I first look at this, and I believe I'm right on this. When n is equal to 3, okay, this will be 9 here, and this will be 5 here, right? You'll be multiplying 364 by some number greater than 1. So how do you get this to be less than 1? They've got something incorrect here. And I have not quite figured out what that is yet. Unless I'm missing something here pretty badly. And for all of those, it seems like there's something screwed up about this. I don't know if they haven't listed it right, because for everything, for every value n greater than or equal to 3, this would be 9 over 5, this would be 16 over 12, and you're multiplying, oh, I'm sorry, I am looking at it backwards. Yeah, that's exactly right. This is a number greater than 364. I was misreading that. I was reading it 664. 364. Yeah, so this is right. But you see those fractions are getting closer and closer to 1. 25 over 21. 36 over 32. 49 over 45. Those getting closer and closer to 1. So when you get large enough n, like 100, that would be 10,000 over 9,996, okay? That's awfully close to 1, so this is getting closer and closer to 364.0. But it does start off at 9 over 5, which is 1.8 times this. 1.8 times this is almost double that. So yeah, that's your Balmer series, okay? Now, it says calculate the limit of it, and again, let me show you that little trick, okay? Find your maximum exponent of your variable, or your index, that's n squared. And what you'll do is do 364.5 over n squared, n squared over n squared over n squared minus 4, and put both of those over n squared. Okay? This goes to 1, that goes to 1, so, and this goes to infinity. I mean, this goes to 0, right? 4 over n squared goes to 0, so you got 364.5 divided by 1 minus 0 is 1. So the limit is 364.5. Never reaches there exactly, but it gets closer and closer and closer to that. Okay? Nanometers, by the way. Now, let's look at a very special kind of a sequence. In this sequence, well, wait a minute. Oh, there it is. The Balmer series, this is figure 7. On the slide is figure 6, but it's figure 7, top of the, above the illustration for Balmer series. I'll go on and blow this up. Okay, remember the Balmer series starts at 3, so that first value is up here around 656, and then the next value is down here, I think, slightly more than 400, and see it closer to 400, but then also getting closer and closer to 365, 364.5. Never actually gets there, but gets awfully close. Now, what you're really dealing with here sorry, these are your spectral wavelengths of hydrogen, okay? And this would be the wavelength of that in nanometers, and then this one. This is a very long wavelength, which is a small frequency, low frequency, which would be in your reddish kind of, I think red, orangey red kind of and then you get into, I think, a greenish type range, and then blues and violets up here. And after a while, there's very little distinction between these wavelengths, so they just sort of smear. You get a very bright spectral line here and here and there, and kind of one there, and after that, they really all blur together. Okay? So those are your wavelength energy you get for various levels when you're exciting a hydrogen ion. Looking at it in your spectrum, along the spectrum, your that first one is toward the reddish end of things. Well, I count this kind of orangey here. Okay, the next one is in the greenish kind of area, then a blue, and then this is a bluish violet or violet type blue, and then the next one's another violet, and they really get so close together you can't really pick them out, and then they go to the ultraviolet anyway. That one won't because it's a 360 and stop, 364.5 and stop. But those are your wavelengths. Those are the spectral lines that you see from a hydrogen ion atom when it's excited. Okay. Now we move to the special kind of sequence. Okay. This is describing a geometric sequence. Okay? Now, you got to have that base for this exponent. That base has to be greater than 1. Don't mess around with negative bases ever. Ever. Don't mess around with 0 as a base. That doesn't give you anything, just 0. If you have small numbers between 0 and 1 as bases, then you're raising that to powers, and things get a little, they're sort of backwards between 0 and 1. If that were equal to 1, again, you get a very uninteresting value. It'd always be 1. So let's pick our r's always greater than 1. Then this is called the geometric sequence. Your a sub n is r to the nth power. And these always diverge to infinity. Okay, if that r is greater than 1, and 1 is going to infinity, there's no way that's not going to go to infinity. I mean, that could be 1.000001, and it might take a bunch of values here, but at some point if that was a small enough r, like 1.0001, it may stay like this for a long time, but then ultimately it's going to go to infinity. Just no way around it, okay? Because you're multiplying a number greater than 1 by itself, basically an infinite number of times to go into infinity. Okay. That's called the geometric sequence. Okay? Now this is the simplest one. The generic one would be, let's see if they get that on the next page. Yeah, there it is. So I won't have to write it. Okay. Here's your f of x or your a sub n. F of x would be CR to the x. Your sequence would be that would be the function. Sequence would be a sub n is equal to CR to the n. Okay, well, for r now, this is your r between 0 and 1. Like I was talking about, things go backwards here. So if r is between 0 and 1, it can't be 0. If r is 0, you just have this value would be 0. Doesn't make a lot of sense. R can't be negative, because if you raise R to a variable power, and that variable power is between 0 and 1, no, I'm sorry, I said that. Yeah, R is between 0 and 1, and that variable power, anytime that power would be 0.5 or the X can go maybe they've eliminated all your restrictions here. But anyway, this is what's happening then. Okay? When you have a very small n, even though R is a small number, if your n is a small number, that C, when R is equal to, when X is equal to 0, this is your X-axis here, X equals 0, this is 1, this is C. R to the 0th power is 1, C times 1 is C. So that's where it starts from. If the R is a number fairly close to 0, then it's going to be a very slowly, very, very slowly declining function, but ultimately it's going to 0. If R is greater to 1, on the other hand, then, I'm sorry, I said that backwards. If R is greater to, close to 0, it goes down more quickly. And the further R gets to 1, it hangs up here for longer and longer and longer. Ultimately, it's going to 0. But you see, if R were 1, then it would just be 1, or C all the way across here. So we're not getting there. And if R is close to 0, that would be 0 all along there. We're not going to go there either. So this is a geometric series that does converge, and it always converges to 0. If the R was greater than 1, it never, ever converges. R is equal to 1, never converges. Okay? Ever. Okay. And I think that's all they're saying in this problem. Let me just see, go back and read the problem again. Yeah. Prove that for R greater than or equal to 0 and C greater than 0, sorry about that. Was jumping down, and I was saying, how did they get there? My eyes jumped down and skipped a couple of lines. Now, let's talk about the R for a moment. That's a geometric sequence. Again, if R is greater than 1, the diverges always to infinity. Between 0 and 1, R converges. R equal 1 doesn't make a lot of sense. It's just the constant 1. So we won't even go there either. But what is that R? Especially if you wrote this as a sequence rather than a function, that would be, oh, I've got to reduce this. F of n would be, or you can call this your A sub n. That would be C R to the to some power. Let's just call it, well, they're leaving it n, so let's just call it n. Okay? Yeah, I'm sorry. They say it down here. A sub n is R to the n. Well, not quite right. This has a C in it, and this doesn't. That's what the problem is here. Since this is a C here, if this is true, then A R to this, that should be C R to the n. It still converges to 0, but they just don't have their C in there. Okay, so if you thought about that written this way, then let's just pick. If n is equal to 0, you'd have, so a sub 0 would be C, r to the 0 is 1. Okay, there it is. Okay, a sub 1 would be C, well, to the 1, so that'd just be CR. A sub 2 would be CR squared. A sub 3 would be CR cubed. A sub 4 would be CR4. And on like this, what do you notice here? The ratio of every term is R. Okay? And that's what they're getting at here. We call R the common ratio. And if you can find a sequence and the ratio between any two terms is always the same value, then you have a geometric sequence. And they call the R the common ratio. Now, they gave you an example here of R is equal to 3, C is equal to 2. So let's see what our sequence was there. A sub n is equal to, I just said it and now I've forgotten what they said. R is equal to 3, C is equal to 2. So that'd be 2 times 3 to the nth power. Okay? A sub 0 would be 2. A sub 1 would be 6. A sub 2 would be, second, 18. A sub 3 would be, it's a little hard to do, 54. Okay? Now the easy way to do that is just your common ratio is your R. Your R is 3. So just multiply, figure out what A sub 0 is, multiply the 3 is 6, 3 is 18, times 3 is 54, times 3 is 162, times 3, you just multiply by 3 every time. You can go back to the form and do it, but goodness, the 2 is the same, the 3 is the same, you just multiply them by one more factor of 3, so just multiply by one factor of 3 there. Okay. Written out, this would be, and that's what they do, I just went on and did it, this would be 2 times 3, 2 times 3 squared, 2 times 3 cubed, 2 times 3, and keep on going. 4th, 5th, whatever. Okay. In the next example, we will determine that when a geometric series converges, recall that A sub n diverges to infinity if the terms A sub n increase beyond the limit, beyond all bounds. Okay? So therefore, the limit as n approaches infinity of A sub n is also going to infinity. If for every value if for every value, every number n, A sub n is greater than n for all sufficiently large n, then we define the limit n approaches infinity of A sub n is equal to minus infinity if you were, while they went to minus. Okay. I'm sorry. I guess I clicked. This is the one I should have been on There, I didn't realize I was on the wrong graph. This is the one where they don't even give you what C is, but this is when it's a diverging sequence. The R is greater than 1, okay? Here is your converging sequence, and that's what I should have had there. The R is something less than 1, okay? And it looks like to me that could be 2, but that's just eyeballing it. I don't know if it is exactly 2. So let's look at example 7 then. I guess we'll do it on this one. Yeah, there's not a slides for this one. I'm going to need to take something for my head. My eyes are giving me problems and it's giving me a headache. So let me pause just for a moment here. Okay. We're getting ready to do example 7. And actually, I guess the previous 2 figures together will show what example 7 is doing. So I could do this on either one of them. So maybe I'll start here. Yeah, because this is R greater than or equal to 0. No. Okay. This is the R greater than 1. Prove that for R greater than or equal to 0 and C greater than 0. Okay? Now what happens when your C is negative? Then every other term becomes negative. Okay? R, remember, you can't have R negative. So if C is negative, then every other term. So then you have something that's going up and down like this. And if your R is greater than 1, then it's going up and down and getting wildly diverging that way. And if it's less than 1, R is less than 1, then whatever it starts, it's getting even closer. It goes above and below the limit. So we don't usually do C is equal to, C is negative. Generally we'll leave it positive. Okay. Now, here's what we're asked to prove, that the limit as n approaches infinity of CR to the n, okay, they've written it correctly that time. Now, this is equal to 0 for any time, wish I'd have started on the other slide now, 0 less than or equal to R less than 1. Now this time they let R go to 0, which of course you can, but that would be C times 0, because any power is just going to be 0. So of course for that, and I've left off my equal sign, let me move these over a little bit. I started writing and got ahead of my writing. It's equal to 0 for 0 less than or equal to R less than 1. Okay. Now, if it's exactly equal to R is equal to 1, okay, then this is going to be 1 to the any power is 1. Multiply that by C and you get C. All right. If R is greater than 1, okay, then this goes to infinity. Okay, there's no choice except that. This is showing the third case here. When R is greater than 1, that certainly takes off and goes, it diverges to infinity. no choice about it. Okay? Now they didn't show the R is equal to 1, but that would then be, now notice this one, here you see, and then it goes up from there. The one they showed next is when it's less than 1, starting at C, and going down from there. When R is equal to 1, it just stays at C throughout. So you've got as R gets closer and closer to 1, if R is a large number, then it departs pretty quickly. Smaller number, it takes longer and longer until finally when R is equal to 1, it doesn't depart at all. So it is, the curves are getting coalescing that way. But then as soon as C gets a little bit greater than 1, a little bit less than 1, then you start diverging from it slowly at first, and then a little bit faster, and the closer you get to 0, the sum that just drops down and becomes 0. Okay, so that's the approach to this. That's visually, and basically all they do is just talk through it just about that same way. Okay, so I think we beat that to death now. Let's go on to the limit laws for sequences. Okay, and these are very similar to limit laws in general. You're just applying them specifically to sequences. So let's see what they are. Assume that the sequence, and this is what it means, to put it in the braces, means that's the sequence A sub n, where A sub n is the nth term of that sequence, and the sequence B sub n, that both of those are convergent sequences, okay? With the limit as n approaches infinity of A sub n will be L, the limit as n approaches infinity of B sub n will be M. L because it means limit, M just as in the next letter after M. So then, if those are the case, those are given, you know they converge, that's what they converge to, then the limit as n approaches infinity of the sum or difference of the sequences A sub n plus B sub n will equal the limit of as n approaches infinity of A sub n plus or minus the limit. So in other words, the limit of a sum or a difference is the sum or the difference of their limits. And if those limits exist, that's going to be L plus or minus M, depending on whether it's the sum or the difference. Same thing here. Even though these may be big numbers, L and M, and the limits are way up there, but they still exist, the limit of the product, as n approaches infinity, is the product of the limits. The product of the limits would be L times M, okay? So even though L and M might be huge numbers, it's still going to be a product. It's going to be even a huger number, but it winds up being a limit. The limit of a quotient, as n approaches infinity of two sequences, will be the quotient of the limits of those two sequences. But if those two have limits, L and M, that will be the case as long as M is not 0. That limit in the denominator here and here and here cannot be 0. Okay? And most of the time our limits are not 0. I mean, most of the time. Quite often you can find things that do not have 0 limits. And then the last one, and this one really combines with this one to make the linearity principle. And this is that the limit of a constant times a sequence is the constant times the limit of the sequence. The limit of the sequence is L, if that's A sub n, so that would be the constant times the limit. So the limit of the constant times a sequence is the constant times the limit of that sequence. And that's for any constant C, no matter how big or how small, that will work. Now, in reality, we don't usually let C be 0, okay? It would still be true, but it has no meaning then. That's just everything 0. All right, now, the next thing, I think we've seen this before in other contexts, limits, think back, long time passing. the squeeze theorem for sequences. They work for limits. Sequence is a limit. So if A sub n is a sequence, B sub n is a sequence, C sub n is a sequence, such that for some number m, okay, capital letter M, that B sub n, okay, is always going to be less than or equal to A sub n, and that's always going to be less than or equal to C sub n. So in other words, B sub n is your minimum of those three, A sub n is the median of those three, you might say, and C sub n is the maximum value of that for all n greater than that value m. Then the limit of B sub n and the limit of B sub n as n goes to infinity, and it happens to be the limit of C sub n as n goes to infinity. These are both the same limit, L. A has no choice but to have that as a limit as well. Because think of it this way, if B sub n is coming along like this and has a limit in L, C sub n is coming along like this and has a limit n, because B sub n is always less than or equal to C sub n for some n past that value m. Back here things could be haywire, okay? But past some point, your C sub n is always greater than your B sub n's, and A sub n is always in between the two. If these two, the outer two of the envelope, are converging to the same limit L, then A sub n has no choice. If it's always less than or equal to C sub n and greater than or equal to B sub n. Okay? Now, I don't think I don't think we have a graph for example 8. Here's what example 8 says. Show that if the limit as n approaches infinity of A sub n, absolute value A sub n, is equal to 0. Then that implies that the limit as n approaches infinity approaches 0 of A sub n. Okay. All right. Now, how do we define absolute value? It's the positive of the number, right? Positive value of the number. So if the number is already positive, it's the number itself, right? If the number is 0, it's the number itself. But if the number is negative, then it's the opposite of that number, right? Because it's always going to be otherwise. So we can rewrite this as the limit as n approaches infinity of A sub n for, let's see, and minus A sub n for A sub n less than infinite, less than 0. Okay, in other words, negative. Wait, I said less than and wrote greater than. Okay, for A sub n less than 0. So this is how we define it. Okay. That's how we define that one. Okay. Now, that's true, but it's not particularly all that, well, we are going to use it in a minute. Let's consider this a sub n here, okay? That a sub n is always greater than or equal to minus absolute value a sub n, and that's always less than or equal to a sub positive absolute value of a sub n. So in other words, sort of a dumb-looking thing, but if a sub n is negative, then that's an equal sign there, right? If a sub n is positive, that's an equal sign. And if a sub n is negative, it's always less than that one, okay? If it's positive, it's always greater than that one. Unless, of course, it's 0, and then they're all equal, okay? So, that's a fact. That is absolutely, certainly, beyond a doubt, true, okay? Now, if the limit of this, well, let's start with this one. This one, we already know is 0, okay? The limit of this one would then be negative 0, which is 0. Well, if the limit of these two is 0, then that limit's got to be 0 as well, squeeze theorem. Okay. So basically, that's how you proceed with that. All right. Now, all these intervening things, we finally get back to our geometric sequence. Okay? And I think this was one that does have a graph to it. So let's do it here. Prove that for C not equal to 0, remember if C is equal to 0, the whole thing's 0. But if C is not equal to 0, that the limit as n approaches infinity of CR to the n is 0 if minus 1 is less than r is less than 0. Okay, so this time, last time I said, for now we're not going to let r be negative. It can be, but it's doing some flopping around some. So this time we are going to let r be less than 0. Okay, but that limit diverges. In other words, it doesn't have a limit. Okay, if r is less than or equal to negative 1. Okay. Okay. Now, I hope you see that this is very similar, almost identical, very similar, we'll say that, to example 7 on the previous page. Okay? The only difference here, they've already said C can't be 0, so we're taking that out of the picture. But if R is a negative number, and between minus 1 and 0, it acts just like it did if that was a positive number between 0 and 1. Okay? That your limit is going to 0. If, however, R is less than negative 1, like negative 2, negative 17, negative anything over there, and you're raising that to a power, then that diverges, but it diverges wildly back and forth because, again, for even ends, those are positive numbers. For odd ends, they're negative numbers. But they get further and further apart, and this is the one that I was showing earlier, or waving my arms about earlier. Okay, so that's what you're asked to show. And again, you'll wind up using probably something very similar to the squeeze theorem there as well. and but it does work. It comes out exactly the same. The difference is with R's greater than 1, just strictly goes up or strictly comes down. With R's less than 1, every other time is positive negative, but either diverging or converging, but it's still going toward the same thing. It could be going up and down and up and down and up and down, getting smaller, or up and down, getting bigger. So basically it does the same thing as the previous does. Now, what this is an illustration of is this, and it's an application of the squeeze theorem, and it's a rather strange one. Sorry. Here is your function. A sub n is equal to 5 to the n over n factorial. Okay? Now, the numerator is what we call a power function. The base is some number, and your exponent is your variable, so to speak. Okay? Actually, an exponential function. Okay? Now, the denominator is, anyone know, I think I said the word, what that stands for? Factorial. What does that mean? Give me an n, any n. 7, okay. Let's say what 7 factorial is. Anyone want to hazard a guess? 7 times 6 times 5 times 4 times 3 times 2, technically times 1, but that's not going to matter any. I'll multiply anything by 1 in itself. That's what a factorial is. Now notice, gets pretty big pretty fast, okay? Now, 5 to the n is what? 5 to 5 to 5 to 5 to 5, however many big n is, okay? So if we start looking at that number, so let's say a sub, you can start with 0. It really doesn't make a lot of sense. You have to define it. 0 factorial is also 1. Strange but true. Okay? So a sub n would be 5 to the 0, which is 1 over 1 factorial would be, or 0 factorial would be 1. Okay? So that's equal to 1. A sub 2, no, that was a sub 0. A sub 1 is equal to, second?
5.
Okay, that would be 5 to the 1 over 1 factorial. 1 factorial is also 1. Okay. So you're right, that would be, I don't know what that second line is here. I think that's pointed, okay, 5 to the 1, and this would be 5. Okay. A sub 2 would be, okay, 5 squared over 2. So that would be 12 and a half. Okay. A sub 3 would be A sub 3 would be, okay, 125 over what, 6? Okay. Looks like it's getting bigger and bigger and bigger, doesn't it? Okay. Let's jump up to the A sub n. Okay. Now what would that be? Wouldn't that be 5 times 5 times 5 times 5 times 5 times 5? Okay, you get the idea? There are n of these. Okay. Okay, there are a total of n of those. So that's 5 to the n. That's your numerator. Your denominator would be whatever that n was. Okay? And you can start at either n, I don't care. Let's start down here. This would be, let's do the 1 here. Could do a 0, it doesn't matter. Times 2 times 3 times 4 times 5 times 6 times, okay, 7 times 8 times 9 times 10. Okay, I stopped at 10 there. We don't need these anymore, right? So, just to keep those out of the way so you don't get them confused with what we've done now. Okay. Now, something to note here. For a finite number of these, this is 5 times 2.5 times 5/3 times 1.2 times 1. Okay? Whatever these are, that's a finite number. For everything past that, this is something less than 1. Right? And the further you go, the smaller it gets, less than 1. Right? So this product of these things gets considerably less than 1. Okay? And this thing up here is just a number. And this is getting smaller and smaller and smaller and smaller and smaller. So ultimately, this is approaching 0. For very, very, very large n's, this sucks. So yeah, this first few, that's 5 times 2.5, that was 10. We did it up here. 12.5 times that one, times that one. They keep getting bigger until at some point, and this is, let's see if they got this right. 1, 2, 3, 4, 5. I think they got it right. 6 being the same but coming back down. And when you multiply all these pieces up, yeah, you get some pretty good sized numbers here, especially multiplying them. But at some point, they come down, 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 and are approaching 0. So the limit for that sequence is indeed a 0. And you do that by the squeeze theorem, that whatever this first one is, you know, it's there. But then you're multiplying that by a number less than 1, that by a number even more less than 1, that, and ultimately you're going down to 0. Okay? Here are those numbers. We started them, but didn't quite finish. Didn't quite get this far, because they're turning out to be decimals. The first one was 5, 12.5, 20.83, and then 26. So this was going up pretty good, a little bit less. This went up by more than a factor of 2. This went up by less than a factor of 2. This went up by very much less than a factor of 2. And look, the bottom fell out. It goes to go out. They skip the 5, 6, 7, 8, and 9. But these would start gradually going down. And at 10, it's down to here. At 15, it's down to there. At 20, it's down to there. At 50, you've got such a small number, you can hardly distinguish it from 0. In fact, most calculators wouldn't even be able to come close to distinguishing that from 0. Maybe some super computers could, but not many calculators. They would count that 0. Okay. And your book actually, no. Okay. Now, here is the proof for that, and this is basically what I was doing with this, they just use a little more of a kind of a terminology. And they reverse the order there. Okay? I was trying to keep your factorials the way we're used to seeing them. They did it the way I was starting to do it. R to the 1, R to the 2, times R over 3, times R over 4, whatever. And you get up to some value, especially up to some value where this ratio is more than 1, but not actually getting less and more close to 1. And at some point then, every one of these are greater than 1, greater than or equal to 1. These are all less than 1. And every one of these is getting closer and closer to 0. So you wind up with some constant here, C, maybe quite big, but then you're multiplying that every time by a factor that's less than 1. So that's going to reduce that C the first time by a little bit, reduce it more the next time, reduce it more the next time, more the next time, until finally somewhere out there this thing is so terribly small that's making that incredibly small too. So that indeed it is approaching 0. So that does converge. Okay. I think we're ready for Theorem 4 now. Goodness, I'm going to have to go put something else in my eyes. A little bit of it is the glare of the white, but I mean, I look at that most days and don't get any problems with it. Here's Theorem 4. If this f of x that you have here, some continuous function, and the limit as n approaches infinity of a sub n is some limit L, then if you were to take this continuous function and operate on that sequence, consecutive members of the sequence, the limit of that function operating on the sequence value, the nth value, would be the function of the, if there's a continuous function, you can pull the function outside of the limit of that. Well, the limit of this is L, so this is then on that being off of L. In other words, we can bring the limit inside of a continuous function. Not a continuous function, no, don't even try it. But if it is a continuous function, then you can bring the limit inside is how they say it. Or take the function of the limit is another way of saying that. Okay. Let's do example 11, which I think demonstrates that, since we don't have a slide for it. Let's go with that. Apply Theorem 4 to the sequence a sub n is equal to 3n over there it is, I lost it for a minute. N plus 1. Okay. And to the function. And the first function is going to be f of x equal e to the x. Okay. Goodness, my pen is dragging sort of badly. Part of it is like x to the n, wasn't it? No, it's e to the x. Sorry about that. Okay. That will be the A part after we do the first that it said. and the b part is going to be g of x is equal to x squared. Okay. Okay. Now, here is a theorem 4. If alpha is continuous, which it is, okay, and the limit as x approaches infinity of a sub n okay, alpha of x is continuous, and the limit of as n approaches infinity of a all right. There's really nothing to do to this original sequence. It might be advantageous to just sort of think what it is. Yeah, well, you're going to have to know the limit of it. So let's do that first. What is the limit as n approaches infinity of a sub n? That would be the limit as n approaches infinity of let's write it down. 3n over n plus 1. All right. Now this is a binomial denominator, so we can't use the real simple way we did before, but the other technique still works. The greatest power of your, I want to say variable, it's not quite a variable, your counter, n, is 1, n to the 1. So we'll divide both the numerator, 3n over n, over n over n plus 1 over n. Okay? Numerator becomes three. First denominator becomes 1 plus 0, and that gives you 3. Okay? So we have done what it says to here. We've shown that what the limit of a sub n is 3. Okay? Now, what we want to do is the limit of the function f of a sub n. Well, your function here, the first f is e to the x. Okay? And if I'm not mistaken, that's going to be e to the a sub n. That's what it actually is heading toward. Yeah, e to the a sub n, which would be, so this first part, the a part, what we're doing is the limit of, as n approaches infinity, of e to the a sub n. A sub n is 3n over n plus 1. Okay, but we've already figured out what that is. This is e to the, and the limit of e of this is 3, so it's e cubed. And that really is all there is to it. I was trying to see if there's some way they want to make it more obvious, but boy, it's just so simple. You just do that, okay? And similarly with the B part, it's the limit as n approaches infinity of a sub n squared, which basically comes out being 3 squared, which is 9. Okay? Yeah. And that's all you do with that. So, I don't know. They made it seem to be a lot more involved than it is. You just plug it in, and it's there. All right. Of great importance for understanding convergence and the concepts of a bounded sequence and a monotonic sequence. So that's the next, not a theorem, but just a definition. Okay. Okay. Say we've got a sequence, A sub n. Okay? Now, if that A sub n, here's a definition. The A sub n is bounded from above if there is some number m somewhere out there that n takes on. Well, I'm sorry. No, some number m, not the n takes on, but the sequence takes on, A sub n. That could be going wildly all over the place, but past some A sub n out here, there's some number m that as long as the A sub n is past that m, for all n, the A sub n is always less than or equal to m for all the n past that point, okay? Then the number m is said to be an upper bound. So if you have this wildly doing whatever it is sequence here, okay, but there's some value m that the A sub n never exceeds. It could touch and be the same as that, but it's always less than or equal to that. Then we say that m is an upper bound for that sequence. Bounded from below means that there's a number little m, such that A sub n, so whatever A sub n is doing here, pick the lowest possible value, and as long as it never gets below this little m, then we say little m is a lower bound. The sequence A sub n is called bounded if it's bounded first from above and from below. And the sequence that is not bounded is called an unbounded sequence. Now, it may be bounded from above and go infinitely small, or it may be bounded from below and go infinitely large. That's fine. Those are both unbounded. It can go wacko in both directions. That's still unbounded. But if there's some m at the top, some little m at the bottom, and it always stays in between there, that's called a bounded sequence. Okay. Now, this looks awfully much like a figure we've seen at least a time or two before. But here is your sequence, the red line. Now, what they didn't say before is that it has to have a limit. So they have said this sequence has a limit. Okay? Now, if that sequence does have a limit, you basically can guarantee it has an upper and lower bound. It's going to be bounded, above and below. Because all you have to do is get this capital M to be greater than the greatest value of M that A sub n can be before it starts zooming in on its limit. At some point, it's going to have to get there, okay? So find the greatest point, whereas the lower bound is something less than the least value that has. There you've got your upper upper and lower bounds. Now those aren't the only ones. If this is indeed is your sequence, you can bring those up until the little m actually intersects that point and the capital M that one. And then if it's has a limit, then at some point it's going to get closer and closer to that limit and never get outside whatever arbitrary epsilon you choose. So you could get actually a larger lower bound and a smaller upper bound, but then when you get that, to reach that point or this point, you can't go any further. But you could go in this direction anywhere you want to. Those are still upper bounds, and anything less than that is a lower bound. Okay? Now, here's the deal. I said, if this sequence does converge, then it has to be bounded above and below, so bounded. If it diverges, it never is bounded. Could be below or above, but never in both directions. Well, let's see. But let me ask you a question. Is every bounded sequence convergent? We know that every convergent sequence is bounded. Just found that maximum, found the minimum, don't stay in between because it's got to be converging in time. Is every bounded sequence, does every bounded sequence converge?
No.
Why not? Give me a counter.
1 over n is the,
No, that is a bounded sequence. Now, when you're talking series, that won't be. But sequence, yeah. But the cosine or sine, okay, that one is certainly bounded by negative 1.1 and positive 1.1, okay? And you can even say minus 1 to 1. It's bounded in there, but it never converges. So yeah, just because it's bounded doesn't guarantee convergence, but if it converges, that does guarantee that it's bounded. So this is theorem 5. They showed us the graph of it first, but here is where they actually state it. Convergent sequences are always bounded, okay? If A sub n converges, then therefore A sub n is bounded. It has to be. If it wasn't bounded, okay, now there's another thing. If a sequence is not bounded, it can't possibly be converged. So you can put it that way, but you can't reverse it completely the other way. Now, an increasing sequence with an upper bound has to have a limit. Okay, now is that an increasing sequence? Okay. All right. If the sequence is always increasing, but it also has an upper bound somewhere out there, it never exceeds it, then that means there has to be a limit. That limit can be less than or equal to that upper bound. Okay. They didn't do the second part, but it certainly would be true. In this case, it looks like it's less than, but certainly the upper bound could not be less than the sequence, because then there would be some point that would exceed that, and it wouldn't be an upper bound anymore. So. Okay. I am having so much trouble seeing this stuff. I mean, with my eyes are giving me fits on this. Okay. Now they give you the table first. In fact, this is example 12. Let's do the theorem before we do the example. whoever put these together, they don't follow the book too well. Goodness, my eyes, I can hardly. I'm not sure. I wonder if I've already had one cataract removed and replaced. The way my eyes are cutting up, I'm wondering if the second one has finally grown big enough that it's giving me problems. This is really painful. Okay, here's theorem 6. Okay. Teaching so many different classes. Have we talked about monotonic yet here? What does the prefix mono mean? One. Okay. And tonic, think of that as direction. Okay. A monotonic sequence is only going in one direction. Strictly increasing or strictly decreasing. No other option. Strictly increasing or strictly decreasing. That's monotonic. If you have a bounded monotonic sequence, okay, that this sequence is strictly increasing, but it's bounded. There's some limit up there, M, that you're never going to exceed, then that has to be convergent. Because if it's increasing and there's some bound up there it can't get past, that means at some point, if it's not that bound, it's something less than that bound, it's going to approach but never reach. But it always has to be increasing. So that would be convergent. But if it was a decreasing, monotonically decreasing, but there was some lower bound, because remember, bounded means up, above, and below. So if it's bounded from below, then it's either going to approach that or something greater than that, and always do. So it's got to converge as well. Okay? So if A sub n is increasing, that's monotonic in the positive direction, and A sub n is always less than or equal to some upper bound M, then A sub n has to converge, and the limit of that convergence of A sub n as it approaches infinity is got to also be less than or equal to M. It could be that limit is M, or if it's not, it's going to be less than M. If A sub n is a decreasing function, strictly decreasing, never stops decreasing or increasing, okay, never does either one of those, and A sub n is greater than some lower bound, and we said it was a bounded sequence, so it has to have a lower bound, then A sub n also converges, and the limit of A sub n is going to be greater than or equal to that lower bound. Could be equal, but it definitely will be greater than or equal. All right, now I need to go back. Okay. This is example 12. Verify that A sub n, which is equal to the square root of n plus 1 minus the square root of n, is decreasing and bounded below. Okay? We're going to show that it's decreasing and bounded below. Okay. Two things we've got to show. Well, actually, third thing. Does the limit A sub n exist? I think you know the answer to that. If it's decreasing and bounded below, it's got to exist. But let's see what we've got here. Now, A sub n is a difference. Give me an n. Pick an n. Second? 6. Okay. So A sub 6 is going to be the square root of 7 minus the square root of 6. Right? Okay. The next one, A sub 7, would be the square root of 8 minus the square root of 7. Right? And A sub 8 would be the square root of 9 minus square root of 8, and so on. By the way, square root of 9 is 3, and you can put that as 3, but I think it's just maybe a little clearer to leave it under the radical and actually evaluate it. Now, later when we do series, we're going to use these same things too, and that really comes up to be something pretty neat. When you look at it, very obvious. Okay? They've done in the table and actually done these calculations for you. They didn't do the 1, but that's really easy to do. Square root of 2 minus square root of 1, square root of 2 is 1.414 minus 1 would be 4.414. Okay? And then a sub 2 would be the square root of 3 minus square root of 2, whatever that is. But you see, each of these is getting a smaller and smaller number. Yes?
Excuse me. It's the windows down.
Oh, yeah. Has it started raining yet?
It looks like it ain't gonna get harder.
Okay.
Sorry for that rush, but I figured you might want to.
Okay. I appreciate you telling me. This morning it didn't look like we had too much chance. Let me pause this. Okay. You can see this is a decreasing function, and it can't ever be 0 because no matter how far up you go, 4,575,000, square root of that minus 1 is going to be greater than 1. Okay? Greater than 0. So therefore, it is bounded from below by 0 for 1, and also decreasing function, so it has to have a limit. Has to. There's no way around that sequence having a limit. Does the limit exist? Yes. Do we know what it is? No, not right off the top. Okay? Now that was just for observation. Can we show it without having to show all the numbers? I mean, maybe somewhere up there, could a sub 455 minus 400 square root of 454, could that actually go up a little bit? Not likely. How can you show that it won't? We'll change this to a function. The f of x that would correspond to this would be the square root of x plus 1 minus the square root of x. Now, how can you tell whether something's increasing or decreasing with the function? Think calculus 1. What do you focus on then? What's the first form of calculus you did? Take a derivative. So let's look at f prime of x. And what would that be? Let me rewrite this one to be x plus 1 to the 1/2 minus x to the 1/2. That's easier to take a derivative in that form. What does that give you? 1/2 x plus 1 to the negative 1/2 minus 1/2 x plus x to the negative 1/2. Now if you go back and write that in radical form, I'm freezing to death here, it would be 1 over 2 times the square root of x plus 1 minus 1 over 2 times the square root of x. Now, that's the first derivative. Now, you tell me, which is this number here, this denominator here, greater than or equal to that. This number here, greater than or equal to that. It's greater than that because it's a little bit bigger. Square root of a little bit bigger number. Got to be bigger than that. Choose the same. So this denominator is greater than that one. So this fraction is less than this fraction, right? Because the inverse relationship. So if this fraction is less than that fraction, this was negative, that was positive, this is always, not just sometimes, always negative. That means the first derivative is negative, meaning it's always decreasing, monotonically decreasing. So therefore, just because this shows you some, this shows you all of them. All of them are decreasing because your first derivative is always negative throughout. And once you've shown that, then and it does have a bound, 0, so therefore it does have to be, have a limit. Now, there is a little trick to show what that limit is. I said they didn't ask for it, and they didn't. But if this is your function, okay, now, this is sort of tricky. Whenever you have something like this, f of x is equal to the square root of x plus 1 minus the square root of x. Okay? If you want to investigate that a little further, anytime you have a radicals like this, added or subtracted, okay, one little clever thing to do is multiply and divide by guess what? Yes, the conjugate of that, exactly. The square root of x plus 1 plus the square root of x, the square root of x plus 1 plus the square root of x. Because that's always 1, right? Okay? Multiplying by the conjugate, what does this give you? That squared, which is x plus 1, minus this squared, which is x over square root of x plus 1 plus the square root of x. Okay, that housetop went way too far, and it didn't erase either. There it went. Okay. Okay. And this is 1. 1 over the square root of x plus 1 plus the square root of x. And guess what the limit of that is x goes to infinity. Well, this is some number getting bigger and bigger and bigger. That's some number getting bigger and bigger and bigger. So 1 over numbers getting bigger and bigger and bigger have to go to 0. So indeed, this looks like there's a limit there. We know that the lower bound is 0, but there's no guarantee, just looking at this, it's going to actually reach 0. That guarantees will reach 0. I mean, it won't reach it, but that's going to be the limit. The lower bound doesn't have to be the limit. In this case, the one we chose was. Negative 17 is also a lower bound, but certainly not the limit. Okay. Let's do number 13. Now, I don't think we have, well, maybe we do. Wait a minute. Oh, yeah. We did this first, and then did the example. Yeah. I was going to say example 13 may have a slide, but example 13 wasn't in the older text. Or was it? No. So this is example 13. I thought that was the thing we just did. Show that the following sequence is bounded and increasing. Okay. A sub 1 is the square root of 2. A sub 2 is the square root of 2 times the square root of 2 inside the house. A sub 3 is the square root of 2 times the square root of 2 times the square root, yeah, that's right, 2, okay? All inside the house, respective houses, and continuing, okay? Show that that is bounded and increasing. So first, how are we going to show that it's bounded? We know this value is about 1.414, right? Now this is 2 times 1.414, okay? Well, that's less than 4. Because square root of 2 is less than 2. So this is less than 4. Square root of 4 is 2, okay? So this thing is less than 2. This is less than 2, like we just said. And 2 times the square root of that is less than 2. So it looks like we certainly have a bound of 4, would you say? Because all those are less than 2. Okay, well, less than the square root of 2. Less than the square root of 4, which is less than 2. Okay? So it has an upper bound of 2. Now, show that it's bounded. Done it. Is it increasing? Well, let's see if it's increasing. This is 1.414. This is something greater than that, of course, because this is greater than 2, but less than 4. And this is greater than 2, but less than, no. This is greater than 2 and less than 4. So this is less than 2, what's inside here. So this is greater than 2 and less than 4. So sure, all these are increasing, okay, because you're multiplying this by something greater than this, okay, and this. So yeah, we're getting larger, so it's increasing and it's bounded, so therefore it does have a limit, because if it's a monotonically increasing function and bounded, it has to have a limit. So we have to find out what that limit is. Now, we've already shown there is a limit, and let's say that limit is way up there, okay? Whatever it happens to be, here's the limit, and this will be the square root of 2 times the square root of 2 times the square root of 2, and you just keep on going, okay? All those. Let these go as long and as far as you want them to go, okay? And just putting more square roots of 2's in there, okay? That's what that limit is, whatever it is, okay? Well, what if we did one more of those? Did the square root of 2 times all that? Well, that would be the square root of 2L, okay? Because this was L, and we did the square root of 2 times that L. See, this thing right here was my L, and then we did one more, so that's the square root of 2 times L. Now, and they did something that, I mean, to me it just looks like it's not possible, but they did it. Okay, let me go back and write it the way they did. That we did one more of those and have, let me take this, wow. And that's equal to what we did when we did that one more time. We did the square root of 2L, okay? And this seems bizarre, but that's what they said. L is equal to the square root of 2L. Now that doesn't seem like they can say that, but they did it, and sure enough, because of infinite series sequence, it is there. Seems like it ought to have a less than or equal there, but they put equals. Okay, so what they do with these two then is square both sides. That'd be L squared is equal to 2L. So guess what L has to be? Okay, let's divide out an L from both sides, and what you get? L is equal to 2. And here is the sequence, at least 1 through 8, and sure enough, that looks like it's getting closer and closer and closer and closer and closer to 2, and it is. All right, homework exercises. We didn't have time to do the preliminary. Y'all okay doing those at home? Okay, so let's do homework exercises number 1, any of the odds 3 through 11. Do 13, any of the odds 15 to 25, any of the odds 27, either 27 or 29 or both. Do 31 or 33 or both, any of the odds 35 to 61, 63 or 65 or both, 67 or 69 or both, and then any of the odds, 71 really doesn't look like there's much to calculate there, but there may be a fair amount good to think about, 71 through 83. Okay, those look very similar to some that we did in class. There's something mentioned here about our arithmetic geometric mean, which has to do with geometric sequences. So let you take a look at that. I don't know if you can find a paper topic there, but you don't have to do anything there. We'll start next time with 10.2, and I'm sure hope we'll move a lot faster than we did at 10.1. Because basically a lot of what we do in 10.2 is based on 10.1, and hopefully then we can get into 11 at least a little bit. All right, we will see you Monday. Have a good weekend. Get those papers and tests in, please. All right, Richard Cribbs never showed. Stuart never was here. And Anthony we haven't seen from almost the very beginning. Yes, sir.
I was going to ask you, when will test 3 be due?
When will we do? I meant to say that at the beginning. Sorry about that. I'll give it to you Monday, and you can get it back to me either Tuesday, Wednesday, or Thursday.
Okay.
But I'd love to, technically it's due on Wednesday, but I'll give you till Thursday. But please try to get it to me by Thursday noon, because I have to have grades in, I think, before noon on Friday. And I've got an infusion on Friday, so I won't be able to do it. I've got to have grades in by the time I leave on Thursday.
Okay.
So the later you get in, the later I have to stay here.
Yeah.
Yeah.
I was going to ask you if I'd be able to email it to you, like the test.
Oh, the test?
Yeah.
You can, but I'll grade what I get, so
Yeah.
if you're pretty confident it'll come through well. Now, let me say this. I can accept, what are the picture files called?
PNG?
Second?
Is it PNG, the image you file you're looking for?
I thought it had a different one on it.
Is it about the
I can, PDF I can print off my old computer, but the JPEG is right.
yeah.
JPEG I cannot, but I can get someone else to do that for me. So if the only way you can send it is JPEG, that's okay. But if you can do it PDF, then that's.
It's almost
I
always
can
easier to do PDF.
What's that?
It's
Yeah.
almost always easier to
Yeah,
do
but a lot of people just like to take a picture with the camera and send it.
Yeah.
It's because I move up to Huntsville
Oh, I
on
see.
Wednesday. So
Okay.
the only day I would have is Tuesday.
Since you're early, aren't you?
No, yeah, I'm moving up.
Oh, okay.
Good deal.
Still for me?